getting started. Okay, so we will quickly recall what is span, right, and the subspaces of R2. Okay, so what are spanning set of a subspace of R2? Okay, so spanning set means that a set of vectors v1, v2, etc. of a subspace S. Okay, and this set is said to be a spanning set if S is equal to span of v1, v2, etc. For example, so can you give one example of a subspace of R2? Anyone? Any subspace of R2?
None the straight line through origin.
Can you please repeat? Yes. Anyone can tell a subspace of R2?
Yeah, ma'am, I was saying a straight line through origin. Am I audible?
Yes, yes, yes. Okay. A straight line through origin. So it can be anything. Y is equal to mx. So maybe specifically let me take y is equal to 3x for example. Okay. So this is a subspace of R2. Good, Aditya. So this your answer is correct. So any straight line passing through origin is a subspace. So I have picked one such straight line which passes through the origin. Okay. So now my set S is set of all x comma y such that y is equal to 3x. This is my set. Okay. Now what can you give some set of vectors which can span this set S? So for example, so if my x value is 1, what should be my y value if it belongs to S? Yes, come on.
3, ma'am.
Yes, right. So in fact, I can even further break this down. So I can write as x comma 3x where x is in R, right? So here you can see that this can specifically be written as, so this is x times of 1 comma 3 x in R, right? So when I break down, this is what I'm getting. So what I can say is that this is equal to span of 1 comma 3, because you see that all the vectors in S can be represented as a multiple of 1 comma 3. So I can write S as span of 1 comma 3. But is just 1 comma 3 a vector which can span S? Can there be any other vectors? Can anyone answer? Can there be any other vector which can span S? Yes? Anyone? Just say some vector from S which is not 1 comma 3. That's all. Give me a vector which is not 1 comma 3 but it is in S.
0, 0.
Okay, 0, 0 is fine. Non-zero vector?
2,6.
2,
(2,6), yes.
very good. 2, comma 6. Right? So you see that here any multiple, in fact, or, so I can write or, more generally, span of alpha comma 3 alpha. So S is equal to span of alpha comma 3 alpha, I can say. Okay, or I can extend it as span of alpha 1 comma 3 alpha 1, alpha 2 comma 3 alpha 2, and so on. But all are multiples of 1 comma 3. Okay, so all these are true. Do you all understand this? Actually, to span the set S, only one vector is sufficient, either this vector or any vector of this form. Okay, so here alpha is fixed. Okay, so any one vector is enough, or if you want to have more vectors also you can have, but the thing is that all will be just multiples of 1 comma 3. So So this set here, so this is your V1, V2 and so on. V1, V2 and so on. Okay. So you see that this is also a spanning set. Okay. This is also a spanning set. This is also a spanning set. So all these are examples of spanning set. So let's say this is maybe U, this is V. So U is a spanning set, V is a spanning set, V1, V2, etc. This is also a spanning set. So do you all understand? How come we are able to find different spanning sets for the same set and why they all make sense? Do you all understand? Okay. So just a question here. Let's see whether you understood or not. Does a spanning set, let's say there are two spanning sets for our subspace. Do they need to have the same number of vectors? Yeah.
Ma'am, can you please repeat the definition of spanning set? I did not understand it.
Yes, sure. See, we call a set, let's say a set of vectors v1, v2, etc. Okay, so maybe some specific finite set also will take. Okay, so now this is, so let's maybe say that this set, some name I want to give. So let me give some name. So what name should I give? Because S is taken here, V, W are subspaces, maybe some set C. Okay, so this is the set C. Now this set, I call it a spanning set if span of this set C is equal to S. Then I say C is a spanning set of S. So here I can take C to be just U or just V or V1, V2, or I can just add V1, V2 up to Vk, where Vk's are simply alpha k, 3 alpha k. Any Vi is given by this.
Okay,
Okay.
so does it mean that the span of V1, V2, V3, either of them is going to be S?
Yes, the span of this set or this set or this, everything is same, which is S.
Ma'am, is this
Okay.
like superset and subset concept?
No, 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 no. So I thought span was covered in the previous session. Was it not covered?
Yes, ma'am. Sir taught us. I'm just asking, is there any relation between, like, it sounds similar, so what's the difference between?
Of course, definitely a spanning set is a subset of a subspace, but spanning set is much more than a subset. Okay. See, what I'm trying to say is that, so for example, so specific, maybe if it is not clear, let me tell you. This is a, this is your R2 plane. Okay. So now let us take the simplest line. This is usually easier to explain. So this is a straight line passing through origin. Now, is this a subspace?
Yes, ma'am.
Okay, so shall we call this as S? Okay,
Okay.
so let's call this S. Now, to generate this line, can I just take any vector from this line and generate?
Yes, it will be a scalar multiple.
Yes, right? So I can take any vector here and I can generate S, and that generating set is called the spanning set. So instead of generating, I am using the word spanning, nothing different. Okay, so if you take some set of vectors and that can generate the whole subspaces, that is a spanning set. Okay, so here if I am taking any vector of the form x comma x, right, alpha comma alpha, that can span S, correct? So instead of just one vector, suppose I want to use two vectors or three vectors, does it make any difference? Anyway, I will be able to get the whole space from the given set of vectors, right?
Right,
Yeah,
but in that case, both should be scalar multiples of each other, right? Because the span here is
exactly.
a.
Exactly. So all are going to lie on the same line, so they will be multiples of each other only.
Okay, got it.
Okay, fine. All
Yes,
right.
got it.
See, when we are moving to higher dimension, having more vectors will make sense. But now we are just in R2. So maximum is for a one-dimensional subspace, you can have minimum one vector, or for a two-dimensional space, you can have two vector. Minimum two vectors is sufficient. But when you move to higher dimensional spaces, this kind of V1, V2, and so on, why we need so many vectors? This kind of a question will be more better to understand. Here you might feel that why only one vector is sufficient, why we need more vectors. I guess that is the question in many of your minds, right? So this is a general definition actually. Here we are not talking just about at R2, but it applies for R2 as well. Okay, fine. Now what
Ma'am,
are
so the spanning set which spans the whole R2 plane will have multiple vectors that are not scalar multiples of each other, right?
multiple? See, minimum we need two linearly independent vectors for R2, yes or no?
Right.
Yes, so that is something minimum, and apart from that we can have as many vectors extra. That does not matter at all, because if we have at least two linearly independent vectors, that is sufficient to span R2. The additional vectors does not even contribute anything. Okay.
Okay, so if I have a set C that is
Mm,
spanning the whole R2 plane,
mm,
then at least two of those vectors will be linearly independent.
exactly, exactly.
Okay, okay,
Okay, same way, every spanning set for a non-zero subspace should have at least one non-zero vector. Okay, so at least one of this vector should be non-zero. Suppose, so let us say if S is non-zero, then at least one Vi is non-zero. Okay, this condition is also needed. If S is non-zero, I should say non-zero instead of non-empty. If it's not the origin, then we need at least one non-zero vector. Okay, so just like you said that we need two linearly independent vectors for R2, so for other subspaces we need at least one non-zero vector. If you are just taking the zero vector, then it's not going to help us, right? Zero vector is an element of S, but it will not be sufficient. Yeah. Okay.
yeah, ma'am, got it.
Okay, fine. So now what are all the subspaces of R2 if you recollect? So the subspaces of R2 can be either origin or straight line passing through origin, which is represented like this, or the entire R2. So these are the possible subspaces of R2, right? So in the first case, so this is your first case, right? So for the first case, so what can be the spanning set? Only the zero vector. If you take any non-zero vector, then it will contribute to some non-zero vector. But for origin, only zero can be the spanning set. Okay. So if your S is zero, then your C should be singleton zero only. Okay. And if your S is a straight line passing through origin like this, then your C can have, just like I mentioned here, one or more vectors on the line with at least one non-zero vector. Okay, so either it can have one or more non-zero vectors on the line. Okay, and for your entire plane R2, you need two or more vectors with at least two in different directions. That is at least two linearly. So here, at least two linearly independent vectors are needed. Clear? Okay, so for different subspaces, what are the possible spanning set is given here. Is that clear?
Yes, ma'am.
Okay, fine, good. So the next thing is, what is the basis of a subspace of R2, right?
Hello.
Yes.
Could you please clarify that what is the substance? I'm not getting it. Maybe I missed the last class.
Okay, see, what are all subspaces? Subspace, what is the condition we need for a subspace? Yes, Nikhil. Yes. Yes. I don't know. Yes. Shanali, what's your doubt?
Ma'am, could you please explain it spanning? I didn't understand it.
Okay. Okay. See, first of all, there is two different things. One is scalar multiplication, and the extended version is linear combination. Okay, these two are the basic things we need to understand span. Okay, what is span of one single vector? Yes, one single vector, suppose u is there. What is span of u? Can anyone tell?
A straight line through origin.
So alpha times, the definition is alpha times of u, alpha in R. So all the multiples of u, correct? So that is the definition of span of one single vector, correct? Yeah. So now what we are saying is that, suppose I am saying that this is your S. Now this is your C. That's all. And this C I am giving a name as spanning set. That's all. So if you understand span, then spanning set is nothing new. So span of U is this S, and for this S, this set U is C is your spanning set. This C is your spanning set. It means what? Any vector from S can be generated using U. If I just have U, then any scalar multiple of U will give me all the elements of S. Okay, that is a spanning set. Okay, that is for one-dimensional spaces. Suppose you are having your entire R2, then you need at least two vectors. So now for two vectors, what is the definition for span? Can anyone tell? What is the definition for span when you have two vectors? So this is when you have one vector, you have scalar multiplication. When you have two vectors, you have what is called linear combination, right?
Ma'am, is
So
it
what is,
alpha u plus beta v?
yes, exactly. So it is a set of all alpha u plus beta v, where your alpha and beta varies over R, right? So now this is your S, and here this is your C. So this is your C, your spanning set of S. So it means what? If you have these two vectors, then any vector in S can be generated by a linear combination of u comma v. The very common spanning set which is considered is, what is a very common spanning set considered for R2? Can anyone say? For R2, 1 0 0 1.
X-axis and Y-axis.
No, they are just vectors, not any axis. I guess I'm not able to write in the end because of some symbol here. We write it below. So 1 0 0 1 is a spanning set for R2. Why? Any element in R2 is of the form x comma y, and I can write x comma y using these two vectors, x times of 1 comma 0 plus y times of 0 comma 1, right? So it means what? These two vectors in the vectors in the spanning set is sufficient to express any vector in the whole set. Do you understand spanning set? So it is kind of a representative of your entire space R2, right? So you have class representatives, right? So they can tell the information about, so if you want to know any information about some member of your class, then the class representative can tell. So I'm just giving some example for you to understand, not very similar, but yeah, they are representatives, you can say. Okay, so they can help you to represent any vector from the whole space. Okay, so this 1 0 0 1. Okay, using this you can express any vector in R2. Same way, if you have two linearly independent vectors, here it is very important that these two are linearly independent. These two are linearly independent is important. Unless they are linearly independent, it cannot span R2. Okay, fine. You understand? Yes? Yes? No? No comments?
Yes, ma'am.
Okay, fine. Okay. Now, one more thing someone asked is that, see, I cannot explain something which was explained in the previous session. Please don't do this again. Just maybe this time I will tell you, but the next time onwards, whatever you have missed in the previous session, go back and see that. If I'm just going to cover the things happened in the previous session, then I will not be able to cover the whole all the topics of the week. Okay. So subspaces are sets from the vector space which satisfies the property that if you are taking any two vector, so let us say you are having a subset of your vector space. Okay, you are having some subset of your vector space. If this subset satisfies this property, okay, so for any two vectors in S, any linear combination should also belong to S. Then such a set is called a subspace. And for R2, the only possible subspaces are origin, any straight line passing through origin, and entire plane passing through origin. Sorry, entire plane, sorry. So if you are taking, suppose for example, if you are taking uh, something which is not passing through origin, okay, so something which is not passing through origin, then this is not a subspace. Why is that so? Because when you take two elements here, add them up, it will not be again the same line. Okay, so it should be, any subspace should be closed under addition as well as scalar multiplication. If you add two vectors, it should be on the same line. If you multiply a given vector by a scalar, then also it should be on the same line. If it satisfies both the property, then only it is a subspace, otherwise it is not a subspace. Okay, fine.
Can we use e to the power x for this example?
E to the power x.
Yeah, or we can't take this.
See, in fact, you cannot take anything apart from straight lines for subspaces here, because we need all the multiples, scalar multiples. Scalar multiples will be only on straight lines, right? That also specifically for lines passing through origin, right? So you cannot imagine any curves here for subspaces. All right.
Okay.
See, we are concentrating on a specific subject called linear algebra. Okay, so that is the hint behind everything. So linear means usually everything is something like a line or plane. Okay, everything is kind of flat here. We don't have curves in linear algebra. It may be an advantage, or some may think it's boring. It's up to you to have a feeling about it. So but yeah, so we are in linear algebra, so you can imagine that most of the things here are just flat, like straight lines or planes. Okay, fine. Linear structures. Okay, so what is the basis of a subspace of R2? Okay, so for basis we need two things. Okay, a set, first of all, a set of vectors is called a basis if, first of all, the set forms a spanning set and the vectors there are linearly independent. Okay, so you have a given set of vectors. Okay, so you have a given set of vectors, so let us call it maybe C. Okay, so this C, if it is both spanning set of S as well as and linearly independent, then we say that C is a basis for S. Okay, both these conditions are needed for a spanning set, right? So for example, let us go back to the same example here. So for your S is equal to set of all x comma 3x, right? X and R. So this is your y is equal to 3x line. So for this, so if I am taking C is equal to 1 comma 3, is 1 comma 3 linearly independent? Any non-zero vector, is it linearly independent? Yes or no? Come on. You
Only
don't know?
multiple of these are linearly independent.
No, no. I see my first page is kind of full because I'm going back and back. I don't know. Okay. See, for linear independence, in particularly in R2, okay. So in R2, what are the linearly? So in R2, okay, what are any linearly independent set? What are the possible linearly independent sets? Linearly independent sets. What are the possibilities? Single non-zero vector. Okay, so this is linearly independent. Okay, otherwise two non-zero vector in different direction. These are the only possible linearly independent sets in R2. Now, do you have a single non-zero vector here? Yes or no?
Yes, ma'am.
So is it linearly independent?
Yes, ma'am.
So this is linearly independent. Is it also spanning S? So,
Yes, ma'am.
right?
Yes,
Alpha
ma'am.
1.
Yeah, it is a spanning set of S. So if both these conditions are satisfied, then is it a basis? Yeah. If both these conditions are satisfied, then we know that it is a basis for S. True or false? True, right?
True.
Yeah, true, right.
True. That is a definition. If it is both spanning and linearly independent, then we know that it is a basis for S. Okay. Now suppose let me take another set. Okay. Now, is this set spanning set? Just go back here and see. I can take multiples also together. That will also span my S. So is this a spanning set for S?
Yes, ma'am.
Yes,
Yes, ma'am.
it is a spanning set, right? But is this linearly independent? Do we have two non-zero vectors in different direction?
No, ma'am.
They are not in
No,
different
ma'am.
direction. They are
These
on
are
the same
linearly
direction,
dependent.
right? So they are linearly dependent. So it means not a basis, right? So this cannot be a basis for S. Understand? Only when both the conditions are there, then only we can say it is a basis. You understand? Yeah.
Yes, ma'am.
Okay. So for the subspace origin, there is no basis. Okay. There is no basis for origin. Okay. Because why we don't have? Can't you argue that since for spanning set we had 0 as a spanning set, can't we say that singleton 0 as a basis for origin?
But
Can,
ma'am, there it is written that it would be non-zero in the definition.
exactly. Exactly.
Zero is
Exactly.
like a point. We can't have a plane with a point.
That's
Yeah,
not
sir.
the argument here. The argument is a
It
basis should be a
it will
linearly
have
independent
infinite
set.
direction.
Yeah, so the basis should be first of all linearly independent. A singleton zeros vector is linearly dependent. This is a linearly dependent set. Remember this. Always a singleton zero or any set containing a zero vector is always linearly dependent. Okay, fine. Always a singleton zero set is linearly dependent. So if you want me to see, I'm tempted to explain, but let me not go back there. Go back to the definition and see why it is linearly dependent. Okay, fine. Okay, so here you see that for origin we don't have any basis. We cannot take 0 as a basis because singleton 0 is a linearly dependent set. For basis we need linear independence. Okay, and for subspaces like this, lines passing through origin, one non-zero vector on the line is enough to form a basis. Okay, so only one non-zero vector can be there in a basis. Can we have two non-zero vectors in a basis for a line passing through origin?
No, ma'am, because
No,
that
right?
No,
will
ma'am.
span the whole. Yeah.
Yes, yes. So it means you see that given a subspace, the number of element in the basis is kind of fixed. Okay, you cannot have more number of elements. Okay, like different number of elements in different bases. You can have different bases, but you cannot have different number of elements in the basis. Right? For example, here you can say that C2 is equal to 2 comma 6. This is also a basis, right? So C1 and C and C2 both are bases for S, but then both are having the same number of elements. So if you take any basis, it should have same number of elements. Okay. And for R2, we said that two vectors in plane in different direction will form a basis. Okay, fine. Now, so for this basis for R2, here is a condition given. So U1 is equal to A comma B and U2 equal to C comma D are a basis for R2 if they are in different directions. That is, they are linearly independent. Okay. So linearly independent means what? Here we will have the condition AD minus BC is not equal to 0. Okay. So what is this AD minus BC? Can anyone recollect? What is this AD minus BC? So the topic of determinants have we covered or not? Sorry, I forgot about the topics in week 1. I guess it is not yet covered, right? Determinant.
But ma'am, if we take a matrices for A, B, C, D, and then if we take determinant, then it would result in AD minus BC.
Yeah, that is
It's a
fine. But
determinant property.
yeah, that is there. But do you all know what is determinant yet or not? Is it introduced or not? In math 1 at least?
Yes, ma'am.
In math 1 you have
The class 7.
in math 1 you have determinants, right? Yeah. So the word
Yeah,
determinant
ma'am.
at least I can use, right? So here you have, suppose A is equal to, okay, you have A, B, C, D. Okay. So suppose you are writing the matrices in the form of, vectors in the form of this matrix, where these vectors are the columns of the matrix. What is the determinant of A? Determinant of A is AD minus
Minus BC.
BC, right? So your AD minus BC is non-zero. If it is non-zero, then we can say that U1 and U2 are linearly independent. Okay. So how this condition came? So if we know that they are like multiples of each other, then what happens? Suppose your CD is a multiple of AB, then what will happen? So let us say, suppose AB, alpha A, alpha B. Now what is the determinant? Determinant is simply alpha times of AB minus alpha AB, right? Alpha AB minus alpha AB. So you see it is 0. So when they are multiples, you see that this becomes 0. So here we can say that if it is non-zero, they cannot be multiples of each other. Okay, fine. So U1 and U2 are in different directions. That is, they are linearly independent if we have this condition. This is a shortcut. Okay.
Means ma'am, if it is a singular matrix, then it would be linear dependent, and if it not is
We
singular
cannot
matrix,
say the
then it will
matrix
be
is linearly dependent. You can say the columns of the matrix are linearly dependent. Yes. Okay, correct.
yeah, ma'am.
Yeah. Okay. So it means what? How many bases can we have then for R2? We can have infinitely many bases, right? So just in so for example, you just take, this is your R2 plane. You take any two vectors in different direction. For example, this is the canonical basis, but actually you can take any two vectors, right? For example, you can take this and this, these two are in different directions, or you can take something like this and this, these two vectors are in different directions, any two vectors in different directions, right? So like this, you can actually choose any two vectors, right? So any two vectors will form, which are in different directions, will form a linearly independent set. So you can easily see that you have infinitely many bases for R2, right? Okay. So another important thing is that any two bases of a subspace of R2 have the same number of elements. This is also something I mentioned, right? And this number has a name, which is the dimension. Okay, so what does mean by dimension? Dimension is the size of a basis of a subspace. Okay, for example, here, how many elements are there in the base in the subspace 0? How many elements are there in the basis for the 0 subspace?
No elements.
No elements. So what should be the dimension?
0.
0.
0.
How many elements are there in the basis for any straight line passing through origin?
1.
1.
So dimension is 1 for any straight line passing through origin. And for the entire plane, how many vectors are there in any basis?
Infinity.
2
Two vectors in different directions.
Yes, only 2
and
vectors.
2
So
dimensions.
dimension is 2. Okay. So here you see that for subspace origin, the dimension is 0. Line passing through origin, the dimension is 1. And for entire plane, the dimension is 2. Okay. Is it clear? So now you can say that, suppose I'm asking, can you say what are all the one-dimensional subspaces of R2? Then you can say line passing through origin. Okay. So this is about subspaces and dimensions, and also about bases we have covered. So now can you quickly try this example here? So here, see, whenever you are having something like this, first try to understand what is this set here. So you are asked to find different bases for this particular equation. So this equation, what does it say? So any straight line passing through origin, what are the different ways of representing line through origin? So line through origin, either you can write it as y is equal to mx, right? Or you can write it as ax
Y
plus
is equals
by
to minus 3x
0.
by 2.
Yeah. So, or simply say that it is alpha times of some specific x naught, y naught. Okay. All these are different ways of writing a line through origin. Okay. So here we are having 3x plus 2y is equal to 0. See, whenever the problem is about finding a basis or finding a spanning set, I recommend you to write it in this way. Okay, this is the way where it is easier for us to find a basis. Okay, so let us try to write it in this form. So here let us say your S is set of all x comma y such that 3x plus 2y is equal to 0. Okay, so what is your y from here? So your 2y is equal to minus 3x. So your y is equal to minus 3 by 2 times of x. So in place of y, I can write minus 3 by 2 times of x. And your x is varying in r. Right? So now I can write it, yes. 1 comma.
Ma'am, 1 comma minus 3 by 2, 2 comma minus 3, and 4 comma minus 6.
Yes. So here you can see that, first of all, how many elements can be there in the basis for this set?
Infinite.
How, I'm not asking how many bases, I'm asking how many elements in the basis can be there.
2, ma'am.
There can see, it is a line passing through origin. This is of a line passing origin, the basis. Is this concept not clear? Why there are not enough responses? See, this is in fact I even wrote it is a line passing through origin. It is of the form ax plus by equal to 0, right? So I just now said that there is just only one element in any basis for a line through origin, right? So here I mentioned, so here you can have only one element for any basis, right? I gave even a specific example. So how many elements can be there in any basis for this particular set? Can you say?
1.
1, right? So
1,
here,
ma'am.
yes. So you see that, for example, here B1 we can have one possibility is exactly the same vector which we are having here. Okay. So apart from this, what other vectors can we take? What other vectors can we take?
0, 0.
See, basis, I just told that the 0 vector should not be in the basis. Right? Please always remember, a basis cannot have a 0
Ma'am,
vector.
2 comma minus 3.
2 comma minus 3. Yes, any multiple of this vector can be there in your basis, right? So for example,
And 4 comma minus 6.
so 2 comma minus 3. So if I'm multiplying this by 2, I will get this. Or if I'm having
4 comma minus 6.
4 comma minus 6. Okay, so if I'm multiplying by 4, I will
And
have
there
4.
are so many bases, like
Yeah, you can
infinite.
keep on adding. Okay, even in fact, you can have maybe, for example, just one more I'm adding. You can just take the negative of it also, multiplying by minus 1. Okay, so all these are bases for, so b1, b2, b3, b4, all these are bases for R2. So not R2, for S. So
For,
here this
S.
is your S.
for this.
Okay, fine. Okay, shall we move on? Is this clear for everyone?
Yes,
Okay.
ma'am, got it.
Okay. So now write down 5 different bases for R2. A very, very easy task. So just take 2 vectors which are from different directions and write it. So quickly tell me. Yes, come on. How many vectors first of all will be there for any basis for R2?
2 vectors.
2 vectors.
Yes. Tell me for what is the obvious one? The usual one, let's say.
1 comma minus 3 by 2.
See, now we have moved to a different problem, R2.
Canonical one, like 1
1
comma
comma
0
2,
and
ma'am.
0 comma 1.
Yes. Then any 2 vectors. See, if suppose let us say this is
No,
my,
ma'am, this is not related with the previous question. This is like completely
no, this is a completely different one.
Okay, ma'am.
Okay,
2
so
comma
let us say,
4 comma 8.
yeah, so you can take like this point. If I am taking this one, then maybe you can take this one, right? Like this randomly, you just take 2 vectors in different direction. That is all you need. You don't have to think much. So for example, this is 1 comma 1 and this is 1 comma minus 1, right? 1 comma 1, 1 comma minus 1. So like this randomly, can you just tell 2 vectors in different directions? So let me write the first vector. Now tell me the second vector.
Minus 2 comma 5.
Good.
And 0 comma 3 and okay, that's fine.
Yeah, 0 comma 3.
And minus 5 comma 7.
Okay, here 1 comma minus 4 and
2
Minus
comma
2
minus
comma
3.
8.
yeah, someone else also said something. What was that?
2 comma 8.
Minus 2. Okay, now
It will be
okay.
opposite.
See, now is this correct?
No, ma'am, it is a scalar multiple, right, of minus 2.
Yeah. See, these
Okay.
two, minus 2 comma 8 is equal to minus 2 times of 1 comma minus 4, right? You cannot have 2 points on the same line. This means what? They both lie on the same line. It means they are on the same direction. So we don't need vectors like this. We need something different. Okay.
Minus
So
2 comma 10.
in fact, so if I simply remove minus here, then are these linearly independent?
Yes, ma'am.
Okay, fine. Okay, fine. Okay, so which
Can
of
we
the,
take 1 comma 2 and 2 comma 4?
you tell me, can we take? Are they
Ma'am,
multiples of each other?
Yes,
yeah,
ma'am.
ma'am.
If
Yes,
they are
ma'am.
multiples, you cannot take in the basis, right?
Okay.
Okay, you cannot take 2 vectors which are multiples of each other. So here maybe I can also write here, note that u1 is not equal to alpha times of u2. Okay, they cannot be multiples of each other. Okay, fine.
Yes, ma'am.
Now which of the following are basis for R2? First of all, in the basis for R2, how many elements we can have?
2, ma'am.
2.
Exactly 2. So obviously A and C and D all are incorrect. Yes or no?
Yes, correct.
Yes. So now for B, are they in different directions?
Yes.
Yes. So let's suppose if this is U1 and this is U2, you can clearly see that U1 is not equal to alpha times of U2. So this means that U1 and U2 are linearly independent. Okay, and hence they will form a basis for R2. Okay, so this is correct. Okay, is this fine?
Yes,
Yeah?
ma'am.
Okay.
Yes, ma'am.
So the next topic here is vector and its basis coordinates. Okay, so it means what? Suppose let us say any vector v in R2. What did we say? Basis means it is kind of a basis or spanning set. They are representatives, right? They are representatives. It means we can express this v as a linear combination of u1 and u2, right? Basis means, first of all, basis means what are the two properties we have for basis? It should be a spanning set
And it should be linearly independent.
it should be linearly independent, right? So if it is linearly independent and if it is spanning, so first of all, any vector v spanning set tells us that it can be written as a linear combination of the basis elements, and linear independence tells that that linear combination is unique. What does that mean by it is unique? So for example, let us go back to the same example. S is equal to set of all x comma 3x. Okay, so let us just go back here. Okay, we saw an example where this 1 comma 3 comma 2 comma 6, this is a spanning set, right? But this is not a linearly independent set, so this is not a basis, right? Now what happens, suppose I am having, let us say, for example, I want to have minus 3 comma minus 9. How can I get this from C1? So let us say this is my U1 and this is U2. How can I write minus 3 comma minus 9 as a linear combination of U1 and U2? Is this that difficult?
So minus 3 u1 and 0 u2. Right.
Minus 3 U1 plus 0 U2. Can we write it in any other possible way? Is there any other possible way? Minus 1 U1 minus 1 U2. Yes or no?
Yes, ma'am. That's correct.
Yeah. So is this linear combination unique?
No, because we just got multiple.
Yes. So we observe that this linear combination is not unique. Okay. So if we don't have linear independence, the linear combination will not be unique. Okay. So the linear independent guarantees that these coefficients are unique. Okay. So here spanning set guarantees that any vector can be first of all expressed as a linear combination of u1 and u2, and the coefficients are unique comes from the property that the basis is linearly independent. So if you have a linearly independent, then the coefficients are unique. Okay, fine. So now if you have any vector v in R2, then this is the only possible way we can write v as a linear combination of u1 and u2. So a u1 plus b u2. So what are this a and b called? So they are called the coordinates of v with respect to the basis u1 and u2. Okay, so what is mean by coordinates of v with respect to u1 u2? It is a comma b. Okay, so we can say that v is equal to a comma b in basis u1 u2. Okay, so now suppose here let's say you have v is equal to 3 comma 5. See, in the just from the first glance this might not be very easy to understand. Let's do more examples and then come back to the definition. Okay, just be patient till you understand. Okay, I will explain with many examples for you. Okay, so now here v is equal to 3 comma 5. Okay, so if v is equal to 3 comma 5 and here no basis is mentioned, so I am assuming that it is canonical basis. Always remember that if the basis is not mentioned, then we are just considering the canonical basis. It means what? In basis 1001. Okay, it means what? 3 comma 5 is equal to a times of 10 plus b times of 01. And what is my a and b? They are the coordinates with respect to these bases, right? What are the
3
coordinates?
and 5.
5.
3 and 5.
Okay, so the a comma b are nothing but my 3 comma 5. Okay, now here is something, some other thing. So v is equal to 1 comma 2 in bases 0 comma 2 comma 3 comma 5. It means what? So here v is some vector x comma y. Okay, and it is equal to 1 times of 0 comma 2 plus 2 times of 3 comma 5. So what is actually v then? Zero
6
comma 2
comma.
plus,
Oh, okay.
yeah, 6 comma,
6 comma 12.
yes. Okay, now here if no basis is mentioned, what does it mean? If no basis is mentioned, it is assumed that we are having the canonical basis. So if it is with respect to canonical basis, will be the coordinates of v change?
No.
No, it will remain the same, right? Yeah. So for b, there is no change. It will remain the same, right? Okay. What about c? For those who wonder, this is why we have no change. Yeah. For c, can you tell? So
So
if b
minus
is
1
equal to,
times minus 1 comma 2
exactly, good,
and 2 times 2 comma minus 1 plus 2
good,
times 2. Yeah.
good. So you have 1 comma
1
minus
comma
2.
minus 2 plus 4 comma
4
minus 2.
comma minus 2.
So 5
5
comma,
comma minus 4.
good, good. All right, good.
Okay, ma'am. So does this mean that I mean the basis of, suppose in the first example, the basis of 0 comma 2 and 3 comma 5 is making the third vector v1 comma 2? I mean, I'm not able to connect the dots here.
See, the same vector, you have different ways of writing the vector. See, how can I say this? See, here what we are doing is that we are visualizing this 1 comma 2 in the basis 0 comma 2 comma 3 comma 5. It means what? Your coordinate axis is kind of shifted to these two vectors. You can say something like that. Okay, it is not very easy to visualize in that way, but something like that. Okay, so if it is just with respect to the canonical basis, you know that 2 comma 1 exactly represents with respect to x how much distance and all that. But this is something like 1 comma 2 in basis 0 comma 2 3 comma 5 means, so you have these are the coordinates with respect to these vectors. So this is 1 times of 0 comma 2 plus 2 times of 3 comma 5. That's all. Okay, so these are like how much linear the exact word is just the coordinates, I can say. It is more meaningful if you go back the other way around. This way it is not really meaningful, but if you go back to the other way, it is a bit more meaningful. For example, suppose you are having, let us say you are having a vector v is equal to c1 c2. Now this is with respect to the canonical basis. Okay, now you want to see how this same vector in canonical basis can be written with respect to a different basis, say u1 and u2. How can we do this?
Okay, so it is like shifting around the whole Cartesian plane in a way.
Exactly.
Okay. Okay.
Okay. So with respect to canonical basis, you know that it is just the same coordinates you see in xy plane. But when it is with respect to a different basis, then you have different coordinates here. Okay. So you can see that. So for example, so here what we see, what is the coordinates with respect to this basis is what is given to us. With that, we see the coordinates with respect to the canonical basis, right? So here what were we having? So for example, let us say find the coordinates of v equal to 1 comma 2 in the following basis. So you have 1 comma 1 and 1 comma minus 1. So what are the coordinates? How will you find? So here you have v is equal to a times of, let us say this is your u1 and this is your u2. What is the definition of coordinates? So if v is
AU1 plus. Okay.
exactly a u1 plus b u2, then a and b are the coordinates. So it means we have to find a and b satisfying this condition, right? So if I'm expanding this, what will I get? So 1 comma 2 is equal to a times of 1 comma 1 plus b times of 1 comma minus 1. So which is a plus b comma a minus b. So comparing the left hand side and right hand side, what are the equations you are getting here? A plus b is equal to,
A plus B equals 1 and A
1.
minus B equals 2.
A minus B is equals to 2.
so when you solve this, what is that you will get? So you will get 2a is equal to 3. So a is equal to 3 by
3 by
2.
2.
And what will be the value of b then? So b is equal to, you will have 3 by 2 minus 2. So 3
Minus
by
1 by 2.
2, so minus 1 by 2. Okay. So the coordinates here are, so what are the coordinates? So they are 3 comma 2 comma minus 1 by 2. Okay. So these are the coordinates of this vector 1 comma 2 in this basis. Now for the next basis, exactly the same process. Now can you tell me? So let us say this is u1, u2. So the same kind of an equation you will have. So maybe I will say cu1 plus du2 to avoid confusion. So let us say 1 comma 2 is equal to c times of
1
1
comma 2.
comma 2 plus d times
3
of,
times of 2 comma 3.
so you are having c plus,
2D
2D.
and 2C plus 3D.
yeah. Uh, so Aditya, I see. Who is the other person trying to respond? I just want to see your name.
Shendan, ma'am.
Shindan. Okay, good. So for the others also, please be interactive. I'm just noticing who are the students who are interactive. I recommend everyone to be interactive. I'm trying to help you all here. Only if you interact and ask your doubts and respond, I will know how far you understand, how much more I need to explain and all. Okay, fine. Okay, so here you have, so what are the equations you will be getting? C plus 2d is equal to 1 and 2c plus 3d is
Equals
equal
to 2.
to 2.
Equals to
So if you are solving this, then you will have 2c plus 4d is equal to 2, 2c plus 3d equal to 2. So
So D
here,
is 0 and C is
So coordinates are 1 and 0.
yeah, so I'm just multiplying this. So what is the answer, final answer?
1 comma 0.
1 comma 0.
1 comma 0.
Okay, so when c is 0 and sorry, c is 1 and d is 0, you have the answer. Okay, fine. Okay,
Yes,
good,
ma'am, got it.
good.
So this is, we are basically shifting it, I mean, keeping aside the technical jargon, we are basically shifting this to another domain where
Yes,
V is equal to 1 comma 2 gets translated into 1 comma 0.
yes, yes.
Okay.
Okay, fine. So the next thing is just we have another extra step, that's all. Now v is equal to 1 comma 2 in the basis, it's not in canonical basis, it's already in some different basis. Then so we have an extra step. First we need to find what is the actual v in canonical basis, then from that we need to again find the coordinates in this basis. So two step is there. So what is step 1? First write the vector in canonical basis. So step 1 is, so you have v is equal to x comma y, which is 1 times of 1 1 plus 2 times of minus 1 1. Right? In basis means this is the beginning.
1 minus 1.
Yeah. So you have
2 into
1 minus 1
2.
is minus 1, and then here 1 plus 2 is 3. Correct?
It should be 2 times 1 comma
2
minus 1.
times 1 minus 1.
Oh, sorry, sir. Yeah, thanks. So you have 1 comma minus 1. Yeah. So it will change here also. So 3 and you have minus 1. This is correct? Yeah. So and the step 2 is the steps we did in the previous step. So now you have the vector in the canonical basis. Right? So now 3 comma minus 1 is in canonical basis.
Ma'am, this question is similar to previous question.
So the step 1 is additional here. In the previous question, you are already having the coordinates in the canonical basis and you are asked to find with respect to a different basis.
Okay.
Now here you don't know what are the points in the canonical basis because it is in different basis here. So first I find the point in the canonical basis and then I shift to the other basis. So now
Okay.
here you have 3 comma minus 1 as a times of 1 comma 2 plus b times of 2 comma 3. Okay, I will give you just a couple of minutes, solve it and tell what is a and what is b. Everyone please do it. See, some may be quick, some may be slow, but the thing is that everyone should try. It's okay if you take more time. Only if you keep on practicing, you will be able to do it more quicker. Yeah? Are you all trying?
Yes, ma'am.
Ma'am, I'm getting
Yes, ma'am.
A to be minus 11 and B to be 7.
Okay, let's see.
Yes, ma'am.
So minus 11 plus 14 is 3 and minus 22 plus 21, yeah, minus 1. So how many of you got the answer or still trying? Just
Ma'am,
give.
got the answer.
Very good. What's your name? I just see the roll number here. Okay, fine. No problem. Good, good. Mahesh, Shunali, Tejas. Good, very good. Yes. What's your doubt, Shoma?
Got the answer.
Good, good, good. See, this is something which happened in one of my sessions. I don't know whether all of you are still like students who have completed your plus 2 recently or something. If there are some senior persons here, if I'm calling you by name, please don't get offended. It happened during one of my sessions that I called by the name and that person was maybe in his 60s or 70s and he got offended. If there are someone like this, please don't get offended. I really don't mean to offend anyone here. Okay, fine.
Ma'am, how did you verify with the answer? Like, where did you replace it and how did you verify with the answer?
Oh, the verification I just did like this. I put A for the first coordinate and B for the second coordinate and saw whether I got the first coordinate. So that is, I mean, minus 11 times of 1 plus 7 times of 2. I saw whether it is 3. Same way I checked whether minus 11 times of 2. Actually, I'm just checking the equations. That's all. Plus here 7 times of 3. Did I get minus 1? This is what I checked.
Okay.
Okay, fine, good. All right. So moving ahead. Good.
Ma'am, would it be possible like to generalize the steps of solving these questions? So, for example, in this one, going from canonical base to another basis, and going from a given basis to canonical basis. Can you just generalize the steps once?
That is what is given here if you want to generalize. So suppose let us say you have a vector in the canonical basis. Okay, so this is some vector c1 c2 in the canonical basis. Okay, and you want to convert it from canonical basis to some other basis u1 u2, where the coordinates of u1 and u2 are here. So to find the coordinates of this vector v with respect to the new basis, you have to solve the system of linear equation. A1x plus b1y equal to c1 and a2x plus b2y equal to c2. Okay, this x comma y is the coordinates of v with respect to the new basis u1 u2. Okay, so here your x comma y is the coordinates of v with respect to u1 u2. Okay, this is what you mean by generalizing, right?
Yes, yes, ma'am.
Okay. Okay, finally we are done with the topics of week 1 and moving to week 2. Okay, fine. So in week 1, you see that we first understood what are vectors, what can we do with vectors, like we can do scalar multiplication, we can do addition, right? And all these vectors in R2, they satisfy the properties of vector spaces. And we saw that what are subspaces of this vector space R2. We saw what is mean by linearly independent vector or dependent vectors. We understood what is mean by spanning of vectors. We understood what is mean by basis, right? And finally, we also saw that how we can express a vector using different bases for which we give the name coordinates. Okay, so roughly these are the topics covered in week 1. Okay, now what we are trying to do is that, so let us say you are having two planes. Okay, two R2s you are having, two different planes you are having. How can we go from one vector in one plane to another vector in another plane? Okay, so this is the beginning. Slowly you can see how can we move from one plane to another space, three-dimensional space or any dimensional space. How can we shift? So in linear fashion, that is why linear transformations. Okay, so that is the next point. And here many of you might think that we have seen separately what are vectors. We have also seen what are vector spaces. So what is the point of doing all this? So in the background, we should always keep in mind we are going to try to solve some system, which is basically system of linear equations somehow comes into play. And you see that link between vectors and system of linear equation comes from linear transformations. Okay, I'm just giving you some motivation. Don't think that I'm confusing you. If it's confusing, just forget whatever I said. Let's go into the topic here. Okay, matrices are crucial to study linear transformations. Why? Because this matrices provides us a way to understand the linear transformations. Okay, we can represent linear transformation using matrices. So you can see that matrices and linear transformations are very closely related. Okay, fine. So you know that 2 by 2 matrix, they have 2 rows and 2 columns. First row, this is first row, this is second row, this is first column, and this is second column. These are some basic information which you already know, right? So now what are two linear equations in two variable means? So it means that it looks like this: a11x plus a12y is c1 and a21x plus a22y equal to c2. Okay, so either you can see this as a linear combination of the column vectors here, right? So this is column 1, this is column 2. So either you can see them as linear combination of the column vectors, or you can see it is the matrix form. So it is like this. So usually this is what we say as a x, the vector x, and here this is usually we say b. Here it is given as c, but anyway it does not matter. So x is equal to b, right? This is the matrix form, right? Okay, so now what are transformations? Transformations from R2 to R2 are functions which take every vector of R2 to some vector in R2. Basically, if you are just saying transformations, they are functions from R2 to R2. Okay, so here you see that it takes every vector from R2 to some other vector in R2. Okay, so you have an input and an output, both are in R2. Okay, so it means what is the domain and codomain here? What is the domain? So function means we should have a domain and codomain, right? So your T is the function here. What is the domain of this function? From where is this input coming from?
R2.
R2. And where is the output?
R2.
Again in R2, right? So it means here the domain and codomain both are R2. Okay. Okay. So now what are some examples of transformations in R2? So for example, you can take the translation. What is mean by translation? You take any vector u, you translate it to translate it by a comma b. For example, suppose my a comma b is 1 comma 2. Then what happens to my 0 comma 0? So my vector 0 comma 0, it get translated to 1 comma 2. Where will my, what is this point? Can anyone say what is this point here?
0 comma 1.
Okay, my 0 comma 1 will go to which vector? Under this translation operation, T of 0 comma 1 is 0 comma 1 plus 1 comma 2. So what is the answer here? 1 comma
1 comma 2. Sorry, 1 comma 3.
Yeah, so it is translated to this vector here. All right. Okay, for example, what is this vector here?
1 comma minus 1.
1 comma minus 1. Where will it get translated to?
Two comma 0.
2 comma
2 comma
1.
1. Sorry.
2 comma 1 or 2 comma 0?
2 comma 1.
2 comma 1.
Yes, 2 comma 1. So here is 2, 1. So here it will get shifted. Okay. So this is the function which we mean by translation. Okay, x plus a comma y comma y plus b. Okay. So this is translation. Okay. Now, what is mean by scaling? It scales every vector by alpha. Okay, so here alpha is fixed. Note that here alpha is fixed. Okay, so it means what? So if you are having any vector, so for example, if you are having, for example, 1 comma 1, and suppose let us say your alpha is maybe 2, then 1 comma 1 will go to 2 comma 2. Okay, or if you are having some other vector, let us say minus 2 comma 1 or minus 2 comma 2, this looks like minus 2 comma 2, the coordinates. If it is minus 2 comma 2 and if I am multiplying it by 2, then it goes to minus 4 comma 4.
Minus 4 comma 4.
It gets translated here. Sorry, it gets scaled here. Okay, so this is what is the scaling operation. Okay, so this is also a transformation. Okay, now what is mean by rotation? So for rotation, maybe this topic we will see it in detail maybe a bit later. For now, you just understand that. So suppose let us say you are having in R2, let us say you are having some vector u. Okay, and this vector, if you are moving it with to an angle of theta. Okay, so this new vector, whatever you have obtained, by rotating it to an angle theta, that is a transformation again. Okay, so we will see more about this rotation transformation a bit later. For now, just understand this much. This is enough. Okay. So u rotated to an angle theta will give you another vector that is a new vector again in R2. So this is a transformation again. Okay. So all the examples, do you understand? Yeah. Yes, Shonali.
So here the distance between from the origin and u will be same, right now?
The distance between origin and
U dash.
yes.
As same as the origin and u.
Yeah. The length is not changing because we are just rotating. The length is not changing. Correct.
Okay, ma'am.
Okay. So now we have seen what are these functions from R2. Some examples of functions from R2 to R2. But we are not interested in just functions. We are more interested in linear transformations. Not just transformation, but linear transformation. So what is mean by this linear transformation? A transformation T from R2 to R2 is said to be linear if TU1 plus U2 is equal to TU1 plus TU2 and T of alpha U is equal to alpha times of TU. Okay. So if these two properties are satisfied, then only we call a transformation to be linear. Okay. So why this condition for is said to be linear? The linear structures are preserved. What does it mean? So I'm just telling you what is happening overall. Because see, these are like abstract statements here, right? I'm just saying what is happening overall. What are the linear structures we have seen in R2? I told this word earlier also. Linear structures means I'm talking about subspaces. What are the subspaces we saw in R2? Before I show, can anyone tell?
Origins, line through origin, and whole R2 plane.
Yes. So these are the linear structures in R2. Okay. If a function can preserve the linear structures, it means what? Under a transformation, if the subspaces will go to only some other subspaces, not to just any random set. Okay, then the linear structure is preserved, right? It means what? A linear structure will get transformed to only some other linear structure. It will not just get transformed to any other random set. Okay, that is what I am saying by linearity structure is preserved. Okay, so this operation here, this function here ensures that the linear structure is preserved. Okay, that I will mathematically is formulated. I will show you that. So I'm just giving you the geometrical view behind this formulas here. Okay, fine. So these two lines here are very crucial for a linear transformation. So everyone should remember these two things. What is the first one? T of u1 plus u2 is equal to T of u1 plus T of u2. So this is the vector addition closed under vector addition property kind of. So this is a scalar multiplication property. Okay. So the first example which we saw for transformation is this. So is this linear? Already it is mentioned that it is non-linear, but why it is non-linear? Okay, so let us say, for example, let us take two vectors. So let us say T of u1 is equal to u1 plus a comma b, and T of u2 is equal to u2 plus a comma b, right? What is T of u1 plus u2? u1 plus u2 plus a comma b. Now what is T of u1 plus T of u2? What is the sum of these two? u1 plus a comma b plus u2 plus a comma b. So now are these two expressions the same or different? Are they same or different? You have a comma b two times. Here you have two times, here you have only one time. So they are not same, right? Yes or no?
Yes.
Right? So for example, here you see that suppose I am taking two vectors. So let us say I am taking, for example, 0 comma 1. T of 0 comma 1 is 1 comma 3. T of what is the other vector I have taken? 1 comma minus 1. 1 comma minus 1 is 2, comma 1. So what is the sum of these two vectors? 1, comma 0.
0.
So 1, comma 0 under this transformation will go to 2, comma 2, right? Yeah. But what is t of 0, comma 1 plus t of 1, comma minus 1? 1, comma 3 plus 2, comma 1, which is 3, comma 3. You see they are not equal. 3,
Ma'am,
comma
3, 4.
Yeah. You see they are not equal. They are not equal. Right? So you see that. So this vector here, let's say this is u1, this is u2. So here you have u1 plus u2, right? And you see that t of u1 plus t of u2 is not same as t of u1 plus u2. So in general, translations are not linear. You understand why translations are not linear? Yes?
Yes, ma'am.
Okay. So the next thing is scaling. So is scaling linear? See, somehow intuition can tell you that it kind of moves along linear directions. So even if intuition does not help, our formula helps. So the formula is that we have to verify these two conditions, right? So what are the two conditions we need to verify? T of u1 is equal to alpha u1. T of u2 is equal to alpha u2. T of u1 plus u2 is equal to alpha times of u1 plus u2, which I can write as alpha u1 plus alpha u2. This is one of the distributive properties you might have seen in the topic of vector spaces, right? So R2 is a vector space, and hence this distributive property is applicable for vectors of R2, right? And then you have T of u1 plus T of u2. What is T of u1 and T of u2? Alpha u1 plus alpha u2. Are they same? Are they same or different?
Same.
It's same, ma'am.
Same, ma'am.
So can we say that T is linear?
Yes, ma'am.
Yes.
No. We need both the conditions to be satisfied for a linear transformation. How can you just skip with one condition? We need to check both. See, whenever you are having multiple conditions for one statement, you need to check all the statements to show that that particular definition is satisfied. But if you want to say the definition is not satisfied, it is enough to just say one of the condition does not satisfy. So just like here we showed that one condition is not satisfied, so this is not linear. But to prove that it is linear, you have to show both the statements, right? So the second statement is that you want, so here I guess alpha is only used, right? For the second one, where is the definition? Yeah, so maybe I'll use some beta. So what is T of beta u? Is, what is T of beta u? Alpha times of beta u. Again, this was one of the distributive properties in your vector spaces, if you remember. So this you can be written as alpha b times of alpha beta into u, right? Now what is beta times of tu? It is beta times of alpha u. So this is beta alpha into u. So alpha beta is equal to beta alpha, right? They are just real numbers, so you can see that they are same. So from this you can see that T of beta u is same as beta times of tu, and hence, so from 1 and 2 you can see that T is linear. So for linearity we need to check both the conditions. Clear? Yes? Yes or no?
Yes, ma'am. Clear.
Yes,
Good.
ma'am.
Good. So the next statement is rotation with respect to polar coordinates. Okay. So rotation, how can we say that it is linear? How can we say rotation is linear? Right now, is it that much easy to see that rotation is linear? See, I'm not able to at this moment with whatever contents we have. I will not be able to give a generalized proof like this, but I am trying to give you a visualization here. Okay. So let us say your theta is 45 degrees now. Okay. So the rotation we are going to do by 45 degrees. Okay. So it means when I'm moving 1 comma, so what is this vector? Can anyone say what is this vector here? Your u is
1, 0.
1, 0. So now where will my 1, 0 be shifted to? If I am rotating it to an angle of 45 degrees in the anti-clockwise direction. To which vector it will move? It will go to, what is this vector here? So it is the vector on the unit circle, right? It is some vector on the unit circle which makes this angle theta equal to 45 degree, right? So here you see that this is a vector on the unit circle which makes 45 degree with the x-axis. Okay, so this is your TU. Okay, now let's take the vector V. Now what is this vector V? Can anyone say?
0, 1.
0, 1. So again 0, 1, when it gets shifted, it is again another vector on the unit circle. So from 45 degrees from here. 45 degrees from the y-axis. So this is your TV. So this is your U, TU. This is your V and TV. Okay. So now what is your U plus V? We know that according to parallelogram law, you know that if this is U and this is V, this should be your U plus V. Right? So your U plus V is 1, 1. Okay. And what is your T of U plus V? 1, 1 shifted to 45 degrees. Right? So when it is shifted to 45 degree, it will go to the y-axis, right? It is this point here, right? So it is this 1.5, 0, 1.5, right? Also, what is TU plus TV? TU plus TV, again by parallelogram law, this should be your TU plus TV, right? According to the parallelogram law, this is your TU plus TV also well. So at least for this specific case, are you able to visualize that T of U plus V is equal to T of U plus T of V?
Yes, yes, ma'am.
Yes, ma'am.
Okay. So in general, this is what will happen. But here, something abstract like this, I will not be able to present because we need, yeah, you can really do it. You have to just represent it in terms of polar coordinates. But right now, let's not do it. Okay. Fine. So here another thing, so this is about the first property. What is the second property? So for the second property, it is easier to visualize compared to the addition property. You see that suppose you are having some vector V, what will the rotation by theta does? It will shift it to an angle theta, right? So what will happen to alpha times of V? Alpha times of V alpha times of V will get shifted to T of alpha V, which is same as, you can see that it is alpha times of TV, right? Okay. So scalar multiplication property is easier to visualize. So both these properties are satisfied for the rotation operation. So rotation operation is a linear transformation. All right. Fine. So here is one homework. Those who are interested, try to see what is the rotation operation, how can it be represented, is it possible to represent it? For this, see, the hint is you need to use polar coordinates. That is the hint. So those who are really interested, try to understand how it can be properly written as a linear transformation. Try to visualize it. Okay, fine. Okay, so here is one important property of a linear transformation. If T is linear, then T of 0 is equal to 0. Okay, so if you are having a transformation from R2 to R2 And if you want to verify whether it is linear or not, the first step is that always check this one before verifying the two properties, addition and scalar multiplication. Before verifying these, first check this one. Okay, if the first property itself fails, then you need not go to the other. But if this is there, then you can check the other two properties. For example, what happens in the translation? What is t of 0? What is t of 0?
A comma B.
And this is not 0. If we have taken a comma b to be non-zero, then you see that t of 0 is a comma b, and that is non-zero. So you can see that t is not linear. Okay, so here we are, remember here, this is non-linear only when a comma b is non-zero. Okay, if a comma b is 0, then t of u equal to u. It is kind of the identity transformation, and that will become linear. So here alpha equal to 1 case, right? So a comma b non-zero case only, this is non-linear. So this is an important property for linearity. Okay. Yes, Sonali.
What does it here means the polar coordinate? Is it the sine plus r cos theta?
Sorry, what?
Scroll up, ma'am.
Yes, I just heard some cos theta.
Polar coordinates here. So it should be in the form of the sine and the cos, right?
Yes,
ma'am?
yes, correct. Okay, fine, good. Yeah, so remember that this is something which all these points is kind of a recall. So to prove that transformation is linear, we need to prove both additivity and scalar multiplication for all points in R2. And to disprove that a transformation is not linear, it is enough if we give one point, whether either it is additivity or scalar multiplication fails. If one of this fails, then we can say it is not linear. You don't have to show both of them fails. If you can say just one of them fails, that is enough. And also, if you see that t of 0 is non-zero, then also you can straight away say that t is not linear. Okay, fine. Okay, which of the following are a linear transformation? See, this is something we can do, but before doing this is a hint which I'm telling you in general. See, everyone please note down this hint. Any linear transformation T from R2 to R2 form T of a comma y is equal to a1x plus b1y comma a2x plus b2y. This is the only possible format for a linear transformation. Okay, so now we can also verify using the properties here, but before that, can you just compare this with this and tell me which of these are linear transformation? The first one, is it of this form or not? Can you say A? Is A in this format?
No,
Yes or no? No, right? Right, it is not of this format. The first one, there is a product of xy. We don't have any product of xy here. So you can see that this one, A, is not linear. Okay, so this is not linear. We'll also see through it through the definition, but this is a shortcut I'm saying. Okay, what about this one? Is this in this
Yes,
format?
it is. Yes.
In fact, you can see what is A1.
A1 is 1, B1 is 1, A2 is 2.
And B2 is
1.
1. Good.
It was two.
Okay. Okay. What about the next one here? This one?
Yes, ma'am. It's a linear.
Yes.
Okay. What is A1 here?
A1
1
is
by
1
2.
By 2.
Yes. And B1 is?
B1 is 0.
0.
And A2 is?
0 and B2 is half.
1 by 2.
Yes. So this is also linear. Good. What about this one?
This is not
No, it
linear.
is a product.
Not linear because product is there, right? So this is some shortcut we are able to see here. Okay, so now suppose here xy and x plus y, what is the other way? So this one I will leave it as a homework, that use definition and verify. The other two will check here. So here, why a is not linear according to the definition? Why it is not linear according to the definition? Shall we check the scalar multiplication property for, because we have already done the addition and seen the example. Let's try with the scalar multiplication. What happens to t of alpha xy? It is alpha
Time of x.
alpha x alpha
Alpha.
y, and then here alpha x plus alpha y, right? So this is what we are getting. So here this is t of alpha times of x comma y. Now what is alpha t of x comma y?
Ma'am, how did you do that? Please explain.
So here if you want one more step, let's add it. So this is t of alpha x alpha y, right? So if I have just multiplied alpha to the vector first, now I am applying the transformation here. So instead of x I have alpha x, and instead of y I have alpha y. That's all. Same thing here. Instead of x I have alpha x, instead of y I have alpha y. Got it? Yes?
Yes, ma'am.
Good, Anand. You asked your doubt. Good. If you are participating in the class, very good. Okay. So alpha times of t of x comma y is alpha xy, right? So because what is t of xy? Maybe here also, because it is the first problem, let me write the steps. So this is t of x comma y, and then I'm multiplying alpha. So it is alpha xy and alpha x plus alpha y. So which coordinate is different when comparing these two?
Ma'am, here is alpha square and here is only alpha.
Yeah, so the change is in the first coordinate, right? So you can see that t of alpha u is not same as alpha tu. So t is not linear. Okay, so using the definition also we can see. Okay, those who want, you can try whether and check whether the first additive property is satisfied or not. Okay, what about this one? For this one, shall we try the additive property? Okay, so if you are trying the additive property, then what happens? So x1 y1 plus t of x2 y2, which is x1 by 2 plus x2 by 2, and then you have x1 y1 by 2 plus x2 y2 by 2. So you will have x1 plus x2 by 2, and then x1 y1 plus x2 y2 by 2. Now what is t of x1 plus x2 y1 plus y2? It is equal to x1 plus x2 by 2, and then here you have x1 plus x2 into y1 plus y2 by 2, correct? So now the change is in which coordinate? The first coordinate or second coordinate?
Then second coordinate.
And second.
Right? So if you call this as u and if you call this as v, then you see that t of u plus t of v is not same as t of u plus v. So t is not linear. Clear?
Yes, ma'am.
So how to check linearity? Is it clear for everyone? This one I have given a homework. Is that fine for everyone? You will be able to verify the two conditions, right? Okay. So those who are confident, very good. Those who are not confident, just give it a try and see whether you are able to do it or not. Okay, fine. Okay. So this is something which I already told you. Can you now tell what is the answer for this? How does a linear transformation T from R2 to R2 look like in general? What is the answer? So I have already told you.
A1x. A1x plus B1y.
A2x plus B2.
A2x plus B2.
Okay, good. Okay. So let T from R2 to R2 be a linear transformation. Then which of the following is RR true? The first one, so here you are having some vector. Here, let's say this is U and this is V. What is U plus V?
2,3.
2,3.
So according to the linearity condition, is this correct? T of U plus V is equal to T of U plus T of V. So is the first one correct?
Yes.
Yes. And second one, for any linear transformation,
Also correct.
yes, T of 0 should be 0. What about this one?
Wrong. 3 into 2 and 0 is not 3.
It should be 0, 0.
Yes. So this is alpha times of U should be equal to alpha times of T of 0. And we know that if T is linear, T of 0 should be 0 comma 0. So this is not correct. Right? Okay. What about this one here? So if this is U, so here let's now split the check this RHS of D. In the RHS, you are having T of 1 comma 2 minus 3 times of 1 comma 1, right, which is T of 1 comma 2 minus 3 comma 3. So when you simplify, what will you get? T of minus 2 comma minus 1. Is that correct?
Yes, ma'am.
So this is also correct, right? So this problem is clear for everyone? Yeah?
Yes, ma'am. Yes, ma'am.
Okay. So here you are given a linear transformation. Now for this specific transformation, what are the conditions? So of course T of 0, 0 is 0, 0. But what is T of 1 comma minus 1? Substitute here and see what is T of 1 comma minus 1. Yeah? What is T of 1 comma minus 1? 1 minus 1 minus 1 minus 1. So 0 comma minus 2. So is this correct then? This is incorrect, right? This part is not correct. So this first statement is incorrect. Okay. What about T of 1 comma 2? T of 1 comma 2 is 3 comma
3, 1.
1. But it is given as 3 comma minus 1. So again it is incorrect. What about T of 0, 1? 1 comma
0.
1 comma?
Sorry, 1, 1.
Yes. So this is correct. What about T of 1 comma 1? 2 comma 0. Right? So this is also correct. Okay. Very straightforward question only. Okay. So now here you are having a linear transformation. If T of 2 comma 3 plus alpha times of T of minus 1 comma 2 is 9 comma 22 for some alpha, find alpha. How can we do this? So here what is that you need to do is that here you have to see, combine these two first of all. T of 2 comma 3 plus minus alpha comma 2 alpha, this is 9 comma 22. Okay. Oh, or maybe you can, sorry, maybe we should have done the other way around, not like this. What is T of 2 comma 3 first of all? According to this, what is T of 2 comma 3?
5 comma 6.
5 comma 6.
5 comma 6. What is T of minus 1 comma 2?
1 comma 4.
1 comma 4. Now what is t of 2 comma 3 plus alpha times of t of minus 1 comma 2? So it is 5 comma 6 plus alpha times of 1 comma 4. So it is 5 plus alpha comma
6 plus 4 alpha.
6 plus 4 alpha, which is given to us as 9 comma 22. So it means 5 plus alpha is equal to 9.
Alpha is 4.
Yeah. So from the first equation, we got alpha is equal to 4. Let's verify it is correct or not from the second equation. So if alpha is equal to 4, 4 4s are 16. So you see that this is satisfied. So alpha equal to 4 is the correct answer. Okay. Is this fine?
Yes, ma'am.
Yes, ma'am.
Okay.
Yes.
So linear transformation and basis. So how can we compute the linear transformation if we know what are the just TV1 and TV2? Suppose we are having some basis for R2. Can we find the transformation if we just know the transformation of only these two vectors? Is that possible? That is the important question next. Okay. So this is very important. Everyone, I recommend everyone to listen very carefully here. Okay. I'm repeating the statement. Suppose you know that T is a linear transformation from R2 to R2 and you know that V1 and V2 forms a basis for R2. You are given the value of T of V1 and T of V2 and you are asked to find what is T of V in general. How do you find it? Okay. For that, you take any V. You know that since V1 and V2 forms a basis, you can write V as a linear combination of V1 and V2. Yes or no? Yes or no? Is the statement and the first step clear for everyone?
Yes, ma'am.
Okay. So next step is that we are asked to find what is T of V. Right? So to find what is T of V, let's apply T on both sides. So T of AV1 plus BV2. Right? So now let's apply the linearity property. So T of AV1 plus T of BV2. Again, we apply the second linearity property. And this are given to us. Right? So if already from this expression, from here, we can find A comma B. You put the A comma B here and these two values are given to you. So now do you get the expression of T of V? Yes. So for any vector V, you can compute the expression for T of V from TV1 and TV2. Is this clear? We will see some examples for this. But up to this, is this clear? Yes?
Yes, ma'am.
Okay, good. So the visualizing part is here. So let us say you have the canonical basis E1 and E2. So this is your canonical basis. Now suppose U is some vector here. Then you know that this is A, this is B. So it means your U is actually A comma B. Your U is the vector A comma B. Okay. So it means what? U is AE1 plus BE2. Right? Now you know that TE1 is this, TE2 is this. So this is given to you. This is the given information. What is TE1 and what is TE2 is the given information. Okay. Now what is ATE1 and BTE2? So let us say this is your, if this is your TE1, so here you have your TE1, this is ATE1 and this is your BTE2. Okay. And here is your TU. Okay, because this is your U is nothing but AE1 plus BE2. So this is your TU. Okay, so this is your visualization here using E1 and E2. Okay, but it will be even more clear if we have some examples. So whether I have added an example here, there should be one example at least. Okay, so maybe for this example, Can you find what is T of V in general? You are given what is T of E1 and what is T of E2. How do we find T of x comma y for this problem? We'll wind up with this problem. So tell me, if T of x comma y, how do you compute from this E1 and E2, T of E1 and E2? What are the steps if you remember? So first step is that how do you write x comma y as a linear combination of E1 and E2? It is x E1 plus, tell me.
Y2.
So you see that T of x comma y is very simple. It is x times of T E1 plus y. Your T E1. 1
1
comma
comma
2.
1 comma
1
And
comma
T
2.
minus 4 comma
Minus
minus
4
8.
comma minus 8.
So you see that it is very simple. It is only this much only. So it's not at all complicated. So if you are given the images of the basis elements, particularly here it is canonical basis. So even more simple here, this computation was simplified because it is canonical basis, right? So you got the expression for T of x comma y. So do you all understand?
Yes, ma'am.
Images of the basis. Okay, so you have more concepts, more topics to learn. So let's not continue further. We have already seen quite some topics today. So just a glimpse of the topics seen in week 2. Week 1 I have already 2 to R2. So translate functions from R2 to R2. So we saw 3 particular examples. One is the translation, next is scaling, and the rotation. And out of this, what are linear transformations is what is our important, what is important to us. So for that, these are the 2 conditions we need for a transformation to be linear. And we saw that out of the 3 examples, only the scaling and rotation transformations are linear, and translation is non-linear if a comma b is non-zero. Okay. And another important property of linear transformation is that it maps 0 vector to 0 vector, right? And then we saw only examples here, and this is also a very important thing. How do a general transformation from R2 to R2 look like? It should be of this form. Okay. And given the images of some basis vectors, how to get the general expression of T of V? For that, first express any given vector as a linear combination of the basis vectors, then write T of V as A times of TV1 plus B times of TV2. Then we get what is T of V using TV1 and TV2. Okay, so only this much we have covered today. I hope the topics which are covered to you are clear. So if it's not clear, please go through the lecture again from YouTube. Try to understand it and come back with your doubts in the next session. I'm happy to clear your doubts if you have. Your participation is what is most expected here. Everyone should participate and learn from here. Okay. Very good. See you all in the next session. Thank you.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.